So you very frequently get subgroups by insisting that they fix something, and then when you compose two symmetries that fix something, it fixes something, etc. Let's do that inside of GLN. So what is the subgroup of Gl2R which fixes the line? If I view Gl2R as acting on R2, what about the subgroup of linear transformations that fix this line? So the line where y equals 0. What is the subgroup that fixes that line? Well, let's think about it in matrix form. Now you can see right away that that has to be a subgroup, regardless of what the matrices in it look like, because these are linear maps of R2 to itself, which are bijections. If they fix this line, and you compose two bijections fixing this line, it fixes the line. Fixing the line means, by the way, just keeping the line on itself. It might move a vector here to a vector here or something, but at least it stabilizes the line. Maybe I should use that expression so that we don't think it fixes every vector on the way. Stabilizing. That's clearly a subgroup, because composition of two things that stabilize this line stabilizes the line. If a map stabilizes this line, so does its inverse. The identity certainly stabilizes this line. So there is some subgroup. What does it look like matricially? So if you have a matrix A, B, C, D, which is invertible, what does it mean that it fixes the first basis vector? It means that the entry B in the matrix is 0. Right? Because this column represents the transformation on the first basis vector, and this column represents the transformation on the second basis vector. And to say that the linear transformation fixes this line says it takes the first basis vector into some multiple of the first basis vector. Right? So the coefficient of the second basis vector in the matrix would be 0. By the way, we represent linear transformations by matrices. So a matrix will fix this line if and only if the B entry is 0. And then we want it to be invertible. So that just means that its determinant is non-zero. So AD is not equal to 0. That's the subgroup of 2 by 2 matrices that fix the line. And then we better check that it's closed under multiplication, huh? I mean, we might have gotten it wrong. So we better check that if we multiply two matrices that look like this, we get another matrix that looks like this. Well, you believe it? We just have to check that this bottom entry is 0, so there's only one thing to check. So we have to go across this row and down this column and verify that the product is 0, and you get 0 times A prime plus D times 0, so the entry here is 0. It's sort of irrelevant what goes up here. So that shows that those matrices are closed under product. Yes? Very good point, but we know that because the product of two matrices with non-zero determinant have non-zero determinant. That's already the fact that it's a subset of GL2. This condition will be, but you're absolutely right. In fact, why don't we check and see what the corners are just to verify that for ourselves. So this corner is A prime, and this corner happens to be D prime, and this thing is much more complicated. And certainly, if A times D and A prime times D prime are non-zero, so is AA prime times DD prime. But good question.